Okay, this is lab report 2, motion of a free-falling object. So the purpose and the synopsis of this lab is analyzing the motion of an object moving in free fall somewhat slowly. And for my video, the analysis occurred over 30 frames, which is about 1 second. And the system of the experiment was a wrapper in air, and then the surroundings was the rest of the universe. And then the main point of the lab was that drag had a significant effect on the motion that will be elaborated on. So for the fundamental principles of this lab, the main one is F net equals ma, Newton's second law. And so the two forces that are being examined are gravity and also the drag force, with the drag coefficient being b, and then speed also being part of the drag force. And then the momentum principle is also relevant. And so for initial conditions and assumptions, so for specifically the first computational model, we're assuming that drag is negligible or zero. And then generally, for the lab, initial velocity is zero in all dimensions, and also the position is zero in all dimensions. And also assume that the object is moving only in the negative y direction. So this is the video of the motion. So these are the data points from the observation. So the total time was 0.98 seconds, while the distance traveled was estimated to be about 0.76 meters. And this is the graph of the observational model, position versus time graph. And it'll be explained later why it's linear. And so for the computational model without drag, the position time graph is a quadratic in the negative direction, while the velocity versus time graph is increasing in the negative direction, and the slope is about equal to g. And this is the model of from the code. And so for the code, the main changes were the fact that of the ball mass, and then the initial conditions were all just zero. Delta t was equivalent to the frames, and then g and the vector were kept the same, and then the proportionality constant was zero, and then the f net was just mg, so that was calculated to be this value. And then for the momentum principle, it was changed to for the velocity, it was changed to the velocity plus the acceleration times delta t, and then for the position, it's just the initial position plus this velocity times delta t, and then these were changed to show the arrows. So for the computational model with drag, the position versus time graph was linear in the negative direction, and then for velocity of time graph, it was an exponential function, which then went into a constant velocity from about 0.2 seconds. And so for the code with drag, the main difference between this code and the other code was that there's now the force of drag, so that had to be calculated. So then the new F net is equal to drag force plus the g, and then everything else was kept the same. And also the proportionality constant was now 0.7, matched with the observational data. And so what does this all mean? So both models predict the terminal velocity. So for gravity, it reached terminal velocity once the motion was complete, once it reached the bottom. While with drag, it reached the terminal velocity much earlier, which was right around 2 seconds. And then if only gravity was present, then the terminal velocity is just when the object reaches the end of the motion. For example, it hits the ground. And if both forces are present, then terminal velocity occurs when the net force is zero. And so what if terminal velocity changes as a result of adding initial velocity? And so when keeping everything else constant, the terminal velocity increases if the initial is in the same direction. So for this motion, it becomes about negative 11 meters per second as opposed to about negative 10 when you add negative 1 meters per second initial velocity. And so takeaways and possible sources of error. There wasn't a lot of error in this lab. The data actually showcased that the effects of drag. And so it also proved that drag is present in real life scenarios in free fall. And also the shape of the object is a big factor in drag. My friends had used a different object, and that object had a lot less drag. So their object was moving faster. And so for the main source of error, since the wrapper was non-uniform on different sides, um, the measurement of the width of the bar probably was not accurate, which affect how much it actually traveled. Thank you for watching.